Welcome to MEI Mechanics. We're on the topic of impulse and momentum 2, collisions in 1D, and this is video 2.4, successive impacts with a smooth plane. So just another reminder about the idea of the coefficient of restitution, which essentially measures the elasticity of a collision, and it's determined by a combination of the two materials involved in the collision. And we define it as the separation speed divided by the approach speed. And it turns out that this can only have a value between 0 and 1, where 1 would mean that you have a perfectly elastic collision in which kinetic energy is conserved, but most of the time this will be less than 1, and so some of the kinetic energy is going to be lost as heat and sound in the collision. Alright, so the change in kinetic energy, defined this way, will have to be negative in such a case. Now, in the previous videos we've looked at objects bumping into each other. In this video we're going to think about a single object that bumps into a fixed plane, so something that's fixed to the ground. Alright, now it turns out we can still apply Newton's laws of restitution in this case. You may be wondering why this is, because it might seem completely different, but if you think about this as really representing the Earth, and you've got a collision between this object and the whole Earth, that's what's really going on there. So if we took that all into account, then we would actually be thinking about conservation of momentum, but effectively, because the Earth's mass is so large, we don't really need to consider conservation of momentum here. We can just assume that the Earth is going to stay exactly where it is in this collision, and so the only speeds involved are the speed at which the object is approaching this fixed plane and the speed at which it is leaving this fixed plane. And so the coefficient of restitution is defined in exactly the same way, separation speed over approach speed, and we go from there. So very simple example to start off with. So if the approach speed is 3 meters per second, E is equal to 1/2, then what that means is that the speed of separation V over the speed of approach, which is 3, is equal to 1/2, and so V is equal to 3 times the half, which is 1.5 meters per second. Very simple in that case. Now let's look at a more complicated example, and we're going to look at this in two different ways, using two different approaches, starting with a SUVAT approach. So we've got a ball which is released from point A at a height of 12.8 meters, and it falls to the ground and bounces, and some energy will be lost in that collision with the ground, so it won't bounce at quite the same height. It will then fall down, hit the ground again, and bounce up to a yet lower height. And given that the coefficient of restitution is 3/4, can we find the height after the second bounce? Now be careful of this diagram. The horizontal axis, even though it's not labelled, the horizontal axis here is time, not space. So the ball is not moving sideways here. This is just representing this ball going vertically, with the horizontal dimension being time. Firstly, take a SUVAT approach to this. So clearly the initial velocity here for the first part of the motion is 0. We don't yet know the final speed, so that will be the thing that we wish to know. We know that the displacement in this part of the motion is 12.8 meters, so we can say that S is 12.8, and if we take downward to be the positive direction, then we can say that A is equal to 10. So which equation do we need? We need the one that involves U, V, S and A, and that is this one, V squared equals U squared plus 2AS. Now remember, U is equal to 0, so we've actually just got V squared is equal to 2 times A times 12.8. That's V squared, and so V is equal to the square root of that, which turns out to be a nice number actually. It's 16 So at this point here, as it's approaching the ground, we've got a speed of 16 meters per second. So after the bounce, well, if the coefficient of restitution is 3/4, well, that means it's going to have 3/4 of its speed after the bounce. And 3/4 of 16 is 12. So it's going to bounce back up at a speed of 12 meters per second. Now, there's no air resistance, alright, so if you can check this yourself by doing SUBET on this, or just make almost common sense will tell you that when it comes back here, it's also going to have a speed of 12 meters per second. Conservation of mechanical energy would also tell you that. So at this point, it's also 12 meters per second. And so after this bounce here, it's going to have 12 times 3/4, which is 9 meters per second. So all we need to do for this final bit now is do another little SUBET. So this time we have U equals 9. We have V will equal 0. The S is the thing we want to find out. We want to know what this final height is. And be careful here. If I've now taken this to be a positive direction, so the acceleration for this part we'll say is -10. Might seem a little bit dodgy changing which direction we call positive, but that's fine because this was a totally separate calculation to this one. And we could change that and we'd still get the same answer. So what we're going to do here, well, we've got the same 4 variables involved, so it must again be v squared equals u squared plus 2as. But v squared is 0, so 0 is equal to u squared, which is 9, plus 2 times -10 times s. If I rearrange that, then I have I've got -20s. Take that over, I'll have 20s equals 81. So s is 81 over 20. Which to a fairly good approximation is 4 meters. Now we said we could do this using energy as well, and there are various stages in terms of how simple we can make this. The main idea is that, well, suppose I call this height h1, and then the speed that the ball has at the end of this drop, we'll call that v1. Now, conservation of mechanical energy tells us that mgh1 will be equal to half mv1 squared. So I could use that then to calculate v1. I could then use my coefficient restitution to work out v2, which will be that speed there. And indeed that speed there will also be v2, passing through a height of h2 if we wanted to think about that at that point. And then again use coefficient restitution to find this v3, which I could then use this to find h3. But there's actually, and it'd be nice to show you this, there's an even quicker way here, which is to say, right, well, from here, what we're really saying, the really important thing, is that the height from which this thing is dropped, or indeed the height that it would reach if it was reversed, is proportional to the square of speed at the bottom of the fall. Alright? And that means if I'm thinking about ratios, so for example h2 over h1, that must be equal to, not proportional now, equal to v2 squared over v1 squared, which is the same as v2 over v1 all squared. Why is that really nice? Because that's e squared. So this coefficient restitution that tells us about speeds, ratios of speeds either side of an impact, it also tells us about a ratio of heights either side of a bounce. Alright, and then by exactly the same argument I can say that h3 over h2 is equal to e squared, and if I combine those two things together, h3 over h1 must be e squared times e squared. In other words, it must be e to the power of 4. So if I want the final height, all I really need to do is do e to the power of 4 and multiply that by the original height of 12.8. And reassuringly that comes out again as 81 over 20, which is approximately equal to 4 meters again. So that concludes video 2.4, successive impacts with a smooth plane, and concludes the topic of impulse and momentum 2, collisions in 1D.